Hello everyone, my name is Al-Afiq Yeong. I hope everybody's having a fantastic time at CppCon this year. First and foremost, I apologize for not being able to be there. Unfortunately, Uncle Sam's appointment books are a bit full at the moment, and I couldn't get the necessary documents required to travel to the US, so I'm kind of stuck in the UK. But regardless, this is a topic that I feel really strongly about. To be honest, in the beginning, it feels like this isn't really an interesting topic to that's worth a presentation. But as I kept seeing more and more people doing the mistakes that I've done, and in fact, even in large production softwares, right, I see this all the time. It really inspired me to give a presentation about this, to share the mistakes that I've made along the way and the lessons that I learned. So, which leads us to our topic today, abstraction patterns for cross-platform development. Before I go into the juicy bits of the presentation, some of you might be interested in knowing me. So, as I've already mentioned, my name is Al-Afiq Yeong. I am a senior systems programmer at Criterion Games. Criterion is a subsidiary of EA. If you're into gaming, you've probably played some of the games that we've made. We've released titles like Burnout, Need for Speed, Battlefield 2042. I'm currently living in the UK, but I was originally from Malaysia. For the curious audience who does not know where Malaysia is, I've included a map. So you can see that teeny tiny dot in America. That should be Aurora, Colorado. It's very hard to get the precision right if you're just snipping the map out with the Windows snipping tool and, taking the marker, putting a dot there. But all the way in the far eastern side of the world, just slightly above the equator, inside of the red circle, we have Malaysia. Being just right above the equator, it definitely is warm and humid. Daily temperatures are about 34 to 37 degrees Celsius. I don't know what that is in Fahrenheit. I'm really sorry for that. Last I've checked, it was a 19-hour flight, flying eastwards. I'm not sure how long it'll take if the plane took off to the west. But yeah, prior to games, I was working in many different industries, mainly as a full stack web developer, except for the 1 year right after graduation where I did C++. But yeah, full stack web development, so your usual front end, back end, databases, and also cloud infrastructure, Azure, AWS, GCN. In terms of interests, not a lot, but I'm mostly interested in low level systems. So memory management, threading, and also data streaming. I am also a performance geek. I always try to squeeze the most performance out of all the softwares that I've worked in. And I wouldn't be in the games industry if I weren't interested in game and rendering engines. There is this saying, give someone a game engine and they'll make a game, but teach someone how to make a game engine and they'll make nothing. So I'm currently in my 2 iteration in my hobby game engine project. I'll make a game someday, but not so soon. Before we begin, let's go over some of the contents that we'll be covering today. So, as usual, as with all presentations, I'm going to start off with an introduction. We're going to talk about the definition of abstraction. We're going to define what cross-platform means in the context of this presentation. I'll tell you why you want an abstraction layer and also some of the challenges that people normally face when you're doing this. And then we're going to go through each of these patterns from the simplest, and then we'll work our way down to the, well, I wouldn't say hardest, but a relatively complex method. And for each of these patterns, I'm going to give you a quick summary. We're going to look at some code in the examples that I've prepared. And then we're going to discuss the pros and cons of each method. So starting from the easiest, we have our best friend, the preprocessor macro. Everybody loves using them. And then we're going to look at something that's much more feasible with runtime polymorphism. Right after that, we are going to look at a technique that is slightly less conventional, but in my opinion, it's a lot better. So using handles and the Pimpl idiom. And then we're going to look at meta build systems, right? We're going to discuss how the meta build systems can help us with creating our abstraction layer. And then we're going to discuss the possibilities of implementing, making it work in runtime, swapping out implementations at runtime. Before I close off the presentation, we're going to go through some tips and tricks that I personally use when creating an abstraction layer. Now, it is worth noting that that you may see many other different approaches to create an abstraction layer in large code bases, but it's usually a mix and match between all of these techniques, and these patterns should give you enough ground for you to start having a better experience when creating that abstraction layer. And then we're gonna close off with a conclusion. All right, let's go to the introduction. Surprisingly, the definition in English is a lot more simpler and shorter than the definition provided in software engineering. I was actually surprised by that, but in English, abstraction originated from the word abstract, which means to dissociate from any specific instance. Quite a clear and concise meaning, if you ask me. Very different from how the language works. But in software engineering, we have a slightly longer definition. The process of removing or generalizing physical, spatial, or temporal details or attributes in the study of objects or systems to focus attention on details of greater importance. It is similar in nature to the process of generalization. So that really long definition, the TLDR, is making code generic and simplified, right? It's pretty much what that means. And usually the term cross-platform is the way how it works in the software industry is that it's locked to a certain meaning. But in the context of this presentation, cross-platform can have a wide meaning, right? It's a spectrum, right? So when I say cross-platform, it can mean multiple operating systems, your Windows, your Linux, your Mac OS. It can mean different API or libraries. So an example in the games industry is that we have so many flavors of graphics APIs to choose from. On Windows, we have 2 already, DirectX 12 and Vulkan. If you're releasing your games on the mobile phones, Android devices support OpenGL and Vulkan. On Mac, they deprecated OpenGL. Sorry, not Mac, but on the iOS, I don't think OpenGL was ever a thing, but they have their own proprietary graphics API, Metal. Cross-platform can also mean different hardwares, whether you're developing your software for the desktop or embedded systems. It can also mean different softwares, right? And what I mean by different softwares is that, for example, in the games industry, when you're releasing your game, it used to be that Steam was the only option for you to buy your games from, but not today, right? That's not really the case anymore. So gamers can buy games from Steam, the Epic Games Store, the Microsoft Store, and each of those storefronts do pretty much the same thing. And they expose backend APIs that you can interact with to unlock a DLC, play with your friend, update an achievement. So it can be considered as different platforms as well. As to why you want to have an abstraction layer for when doing cross-platform development, because mainly it exposes a single source of truth to your users, right, your clients. Now, before I proceed, I feel like it's really important for me to define what a client means in the context of this presentation. So in large code bases, not everybody owns all of the code. usually what happens is that different teams will own different portions of the code. And if another team have to use functionalities that's part of your responsibility, you have to expose an interface for them to interact with. So when I say client, what I mean is the different teams that use your API/interface. All right. The next thing is that it becomes easier to maintain in the long term because it prevents code divergence. Also, it saves development costs. Of course, there is that initial upfront development costs, which can be pretty costly. But as with all things software engineering, the initial upfront cost is always expensive. And also, it enables new opportunities to the business. So imagine you already have the abstraction layer, and then you want to support a new platform. Well, you already have the skeleton. You already have the structure. So all you have to do is just extend it. So with the challenges, as with all software designs, software design, especially when it comes to abstraction layers for cross-platform development, it is generally difficult. You really need knowledge of all the platforms that you're going to support. And also it requires a lot of planning, not by one person, but hopefully, ideally by a team of people that you can plan around with. Also with when creating an abstraction layer, it takes a while to strike a balance because each platform would have their own nuances that you might need to consider. Ultimately, all of those platforms do pretty much the same thing. It's just that some of them have nuances that they take to do to reach the same outcome. So because of that, it usually takes a while for your abstraction layer to strike a balance, right? So without further ado, let us proceed to our first pattern, preprocessor macros, right? Everybody loves to use them, although they are extremely discouraged, but people still use them. People love to use them. So with preprocessor macros, it is the simplest way to abstract cross-platform code. In fact, I would argue that it is the first method that any C++ engineer would immediately think of when they're starting out, right? Because it's there. If you're working on an existing code base, you'll see plenty of that. And because of the way how it works, it becomes very intuitive for people who are starting out to think about this. And also with preprocessor macros, it works really well on small pieces of code. Right, so let's take a look at how it would work. So this is an example that I've prepared. I've written out all the code. Before I begin, let me give you some context of what we're trying to do. Since I come from a games industry background, and I am very familiar with writing rendering backends. So this is the example that we'll be using. We're going to create a graphics device that lets us interact with our GPU or integrated graphics device in your CPU. So we're going to create a device. We're going to try an initialize device. And because of how each API is, even though they do the same thing again, but some might be more verbose than the other. So it is the perfect example to showcase the challenges that we'll be facing when doing cross-platform development. So as you can already see, I've declared two preprocessor macros. One is use Vulkan, the other is use DirectX. Immediately, you can see that on Vulkan, you actually need to have an instance, a physical device. Only then you can initialize the device. Whereas in DirectX 12, you can just need to store a pointer to the device to actually start initializing the device. So depending on which macro is defined, I've included separate header files. With Vulkan, I've included Vulk. Vulk is just a wrapper around the Vulkan loader. And then if we're using DirectX 12, we include D3G12. And the interface that we're trying to create, like as I've already mentioned, we're going to initialize a graphics device. So the interface I'm exposing is create graphics device. Now, ideally, this would be in a separate header file, but for the sake of simplicity, we're just going to be included in main. But you can imagine, you have a header file with all the interface that you've defined, and then in the body of the function, in the function's definition, what you would do is you would do pound if and the macros that you've defined, and also pound else if on the other platform macro that you're defining, and you would write the platform specific code inside of the preprocessor block for each of those macros, like what I'm doing over here. So you can see use Vulkan. I'm creating a Vulkan application, creating an instance, selecting a physical device over here with the GPU, and lastly, I created a Vulkan device, right? But in DirectX 12, as you can see, what I need to do to create a device is to just do this, right? It is a lot more shorter, a lot more concise, I would say, right? It's not as verbose as Vulkan is. So this is what I mean when I say that even though different APIs, different platforms do the same thing, some of them have nuances that make them slightly more tedious than the rest. And then in the main function, we're just going to call create graphics device. So that is pretty much how you would abstract away code with preprocessor macros. Now, let's move back into the slide. If you haven't already noticed, you should avoid this at all costs. From the example, it's very easy to start guessing the problems that you face along the way. But I'll just highlight a few that's very prevalent when you use this technique to abstract code. The function body can become really, really long. That is just one example, which is creating the graphics device. When it comes to graphics programming, creating the graphics pipeline would take a lot more lines of code, right? And I'm sure it's the same for any other field. So the function body can become really, really long, especially with more platforms you're supporting. The size of the function body can grow exponentially, and you can already see from the example that I've presented is that it ruins readability, right? It's very difficult to follow. That's not even the worst part, right? The worst part is that when you're merging code, it becomes a tedious job when you have to consider different platforms in that one function body. And because of how a lot of merge tools work, they usually just compare line by line. There is a possibility that they might detect change from a different preprocessor block that maybe you didn't even make in the first place. Aside from that, very ugly code structure, there's macro pollution everywhere. And the most problematic part when using this method is that it requires the preprocessor that you've defined to be exposed to other libraries. So in your build system, you could usually define a certain set of macros, but it's usually self-contained, right? It's always private to its own project. But in a actual production software, right, in large code bases, there's usually a lot of projects. I've seen companies that have 200 projects in a single solution. I've seen companies that have about close to 1,000 projects in a single solution. So if you want to make the abstraction layer work, you'd have to expose the preprocessor definition to all the projects that you're using. And that is just bad engineering practice in general. So the moral of the story over here, the quickest summary that I can give is that there are better ways to abstract code, and you should try avoiding using macros as how I've showed in the example. So let's move on to something that's much more feasible, much more interesting, right? Which is runtime polymorphism. Now, with runtime polymorphism, things do become better. the way how it works is that you would have an abstract base class. Ideally, it should be abstract because you don't really want to instantiate an object of the abstract base class. It has no meaning because it is not aware of the platform that it's on. You would have an abstract base class with the interface that you want to expose to the clients defined as pure virtual functions. And then for each platform that you are supporting, what you would then do is you would create a derived class for that specific platform. You would override the methods to contain the logic for the platform that is specific to the platform. I'm sure everybody already knows how runtime polymorphism works in C++, but for the sake of this presentation, we're going to have a quick refresher. So whenever a class function has the virtual specifier, the compiler generates a vtable for the class. Now the vtable is just a lookup table of function calls resolved at runtime, and the vtable only exists for each type of class. So what that means is that if you have two objects of the of a same class, of a derived class that has a virtual method, it will still point to one vtable, which is the class's vtable, right? And aside from the vtable, the compiler also generates a hidden virtual pointer that points to the virtual table or that class. So how you would then implement it in code is something like this. So again, still in the realm of graphics because it is the field that I am most familiar with and has it exposes all of the challenges that people normally face when doing cross-platform development. So with runtime polymorphism, what you'll have is you'll have an abstract base class. Over here, I've declared the device as an abstract base class. We're still going to initialize the device. So the initialize method is declared as pure virtual. And then for each platform that I'll be releasing my software on, right, I have a derived class with all of the implementation details for that specific platform. Now notice with this method, I've included the platform-specific header files along with the derived class's header file, right? I've included all the platform-specific details inside of the class's private scope. And I've overridden the interface that I've provided inside of the base class to contain the logic that is specific to the platform. So if you can see in Vulkan device or CPP, the initialize function contain all the verbosity that is required to initialize a Vulkan device. And inside of DirectX 12, the initialize function contain all of the simplicity that is required to create a D3D12 graphics device. Now, as to how you would use it, because of how it works, because we're using runtime polymorphism, we're able to pass the pointer to the base class object around. What this allows is it allows the clients to access the interface in a platform independent context. But before we do that, we have to instantiate the object, the derived class object that is specific to the platform, and have the pointer to the base class point to the address of that platform specific context object, right? Context class. So over here you can see I have a stud unique pointer that is assigned to a Vulkan device, right? The unique pointer holds the base device pointer. And then what I can do is I can then access the initialize method in a context independent manner. So with runtime polymorphism, it is definitely an improvement over using preprocessor macros, and the biggest benefit is that it is a language feature, right? Aside from preprocessor macros, it is the second thing that is the easiest to get started with, and theoretically, with this method, you are able to change implementations at runtime. If that is something that your software has to support, This is one way to do swapping out implementations at runtime. And because we've already defined the structure of the interface inside of the base class, what this allows us is, we're always exposing the same set of interface regardless of the platform that we're on to the clients, right? So there is consistency between all the other platforms if we use runtime polymorphism to create our abstraction layer. And what this allows us is, to in the client code, it allows consistent and non-divergent paths in their code base, right? Because the object can be passed around as a pointer to the base class object. They still can access the methods because having the vtable will just resolve to the correct function call. Now, obviously, runtime polymorphism is not free. It has a performance cost to it. There will always be a vtable lookup every time a virtual method is called. Normally, well, not normally, depending on how you pass the pointer to the object around, the compiler can devirtualize, but not when the object is passed around as a pointer to the base class object, right? The compiler cannot make assumptions that that the pointer is not referencing a different derived class type. I'm sorry if I butcher his name, but Ivica has made a fantastic presentation. He gave a fantastic presentation, I think it was last year, about the performance price of virtual functions. I highly recommend everyone to go listen to his talk. It's very informative and really opens up your mind about runtime polymorphism. Also, with this method, the final executable still contains code from the other platform implementations. And for something as trivial as graphics API, it's not that important. But if you're releasing, say for example, you're releasing your software on Linux, but pieces of your code still have, and it is a software that you have to pay for, and pieces of your code still have portions that are specific to Windows, users can get really creative. So it is definitely a problem if you want to keep your software strictly on a specific platform. Also, with this method, there are compilation dependencies. We've already seen that I had to include the platform-specific header files inside of the derived class header files. And, if you have to change an interface, not only in the base class, but also in the derived class, if you do a recompile, because it's a header file, the compilation does take a little bit longer to resolve. And the thing about runtime polymorphism and using preprocessor macros is that, platform-specific information gets leaked out to the client side. So what I mean by leakages in the slide is that if I go back to my example and I type something, if I try to access a type that is specific to Vulkan, so say PK instance, I can access it. So imagine you are a client in a very large code base that is including my header, the implementation, or that is including the implementation for a specific platform. I can simply access types or objects that are specific to a platform, right? As you can see over here, I have access to VK instance. Not only that, I can access things from DirectX12, right? The command allocator, for example. So you don't really want to do that. You want to keep your implementation self-contained. You don't want the platform-specific details to start leaking out into the client's code base. So it's 2023. I believe there are better ways to do things. So let's try something else. Now let's move on to a method that personally I find it more interesting than runtime polymorphism, and I personally use in my personal projects. Let's talk about Pimpl and handles. No, the Pimpl that I'm referring here is not the Pimpl that grows on our faces, but rather the Pimpl that is pointer to implementation. So before I talk about handles, I'm gonna briefly explain about Pimpl. As we mentioned before, Pimpl stands for pointer to implementation. The way how it's usually done is that people will store a void pointer inside of the interface's private scope or public scope if you want to give public access to the pointer. And then inside of the interface's CPP file, you define a class that contains all of the platform-specific information. You would then instantiate that object and have the void pointer point to the address of that instantiated object. Now, with C++ being a strongly typed language, type punning can be frowned upon in the community. So the other way that you can do about this is to substitute the void pointer with a forward declared class, right? Have a pointer to a forward declared class. And this works because the size of a pointer is 8 in x64 and 4 in x86. It's consistent, right? The gist is that the size of a pointer is consistent throughout the program's lifetime, or is already known by the compiler beforehand. And then this basically allows the compiler to actually compile the program. And then for each platform that you are supporting, you would then define the forward declared class that contains all of the platform specific information and do the same thing, right? Instantiate the object and have the pointer point to the address of the instantiated object. Now, if the lifetime of the resource is important or you would like to have it automated, you can substitute the raw pointer with a split unique pointer, and it would just work the same. So let's take a look at how it would be implemented. So same thing again with the graphics device. We do want to initialize a graphics device. You'll immediately notice that I no longer contain platform specific header files inside of the interface's header file. And in fact, all I only have is memory because I am using split unique pointer. Same thing again, I'm exposing the initialize method. But the good thing is that, the device class is no longer polymorphic. All we have is just a forward declared device context. I should probably mention that to make this work really nicely, the forward declared class should have a name that is independent of the context that it's going to be in. And then for each platform that we're supporting, over here you can see I have two folders, DX12 and also Vulkan. I have a device.cpp file for each of them. And in each of these CPP file, what I have is a definition to the device context, right? Aside from that, I included the platform-specific header files. But the main thing is that I've defined device context to be different depending on the platform, right? And this is what it looks like in DX12, again in Vulkan. And then inside of the initialize method, I've basically contained the function body with the logic that is required for the specific platform. Before I did that, I did instantiate the object I did instantiate a device class object and have assigned it to the unique pointer. The same thing really with DX12, instantiate the device context that contains all of the information I need for DX12, assign it to the unique pointer, and also create a D3, D12 device. The benefit is that now, whenever we're using this, all we have to do is to just declare the device. It's no longer polymorphic, and we can just initialize the object, and it's still in a platform. It's no longer how do I say this? We can still initialize object free of the platform's context, right? Now, for the eagle-eyed viewers, you probably noticed something is wrong, right? You probably noticed that there is something wrong with this method, but I'll get to it in further into the presentation. But first, let us talk about handles. A handle is a type, usually an integer, that represents an object that is stored somewhere in the program. So rather than returning a pointer or a reference to the object, you return a handle instead. This really helps with ownership because we no longer have problems with ownership to a resource. And a handle can be as simple as an int or an unsigned int or a size t, but that itself wouldn't be meaningful because it has no meaning to the resource. So what people usually do instead is that they will provide a strong type integer value as a handle. So with handles, it is small and cheap. It is a small and cheap method to represent that an entity exists in the program. And generally in cross-platform development, all we really care about is the existence of a resource rather than the details. If we do need the details, what we can do is we can introduce a new function that takes in the handle, get the resource from a resource pool, and then decode all of the platform-specific information in a way that is platform agnostic, right? We can present the information in a way that is agnostic of the platform that it is on. So with handles, this is what you'll normally do. We have a handle class. This is really just a strong type class, right? That takes in the value that we are storing. And a second template argument that I call resource name, but you can call it anything else, but I call it resource name. And all the second template argument does is just to provide the handle with a strong type interface. So what I mean is that now, again, we are going to create a device manager. The thing about handles is that it works really well with factory methods. So now we have a device manager that returns a device handle whenever we create a new device. You'll notice that I've included handle.h. Like I said, the second template argument is to just provide a strong type interface to the type that we're storing in the handle, which is a size t, right? I've aliased the handle to be device handle. So whenever we create a new device, I return a device handle instead. And if I need to initialize the device, I have a function called initialize device that takes in a device handle. Inside of initialize device, all it does is that it validates that the handle is correct, and it is correct to let me access the resource that I'm storing inside of my resource pool, which is still vector over here. And then if the handle is invalid, I return false, or you could do some other sorts of validation over here, report an error, or log it into the logger. But if the handle is valid, I get the value that is being stored in the handle. I use that to index into my resource pool and call the initialize method for the device. So there's definitely a lot of pros to using this methodology. One thing, and I feel like this is the biggest, is that our code base can no longer contain can no longer have leakages from the specific platform we're on, right? Because the platform specific header files are no longer stored in the interfaces header file, but rather in the platform specific interfaces CPP file. We no longer get leakages. Also with Pimpls, all of the implementation are self-contained inside of their own CPP file. And the best thing about Pimpl is that you no longer introduce compilation dependencies because the platform-specific header files are no longer stored inside of the interfaces header file. So whenever you're changing the interface or updating the interface, it no longer requires a full recompile. And in terms of performance, it's not as great as runtime polymorphism because there is no longer that vtable lookup. In fact, the only performance cost there is to this is that initial cache miss when fetching the pointer from memory. But as I mentioned before, for the eagle-eye viewers, you probably already know what's wrong with this. What's wrong with this method? Our program no longer compiles. Because we've provided two definitions to device context for different implementations, we've essentially broken the one definition rule, right? And our program can no longer compile. So language feature-wise, we've hit a wall. There is nothing else in the programming language that lets us fix this. So this is the perfect time to start talking about meta build system, which is our next topic. Let's talk about meta build systems. Yay! If you don't know, meta build systems can be intimidating at first, but I would argue that they are necessary evil. A programming language today is not just the syntax and the rules. In my opinion, the development experience should be considered as part of the programming language. And in C++, we have meta build system. Now, a meta build system is a system that provides platform-independent script to generate build script depending on the platform. A meta build system could also generate the target build script at runtime. So I would say it is natural for C++ engineers to start being involved in meta build systems, getting their hands dirty, working with meta build systems. Further into the career, as I've already mentioned, they can be intimidating to start with, but after a while, you can easily get a hang of things. And the thing about meta build systems is that they help us with generating solution files, right? Forgive my Microsoft terminologies, but it is what I'm used to work with. It helps with generating solution files. But aside from that, it also helps with the project's configuration, right? Depending on the different builds, you can have different include paths. You could have different compiler flags. You could even customize certain build types, right? You don't have to restrict yourself to debug or release builds. You can have release builds with debug symbols. You can have partially optimized release builds or partially optimized debug builds. In case if your program runs really slow in debug, that's the case with most games. A meta build system also helps in terms of project structure. So the file organization in a project, for example, in Visual Studio CMake target view, depending on how you've defined the CMake list or TXT, it helps with file organization. But this is the part that we're really interested in, right? With a meta build system, it allows us to configure or to include certain files or even exclude certain files from different configurations, right? We can introduce a configuration that is specific to a platform and assign and inside of the script, we can detect what configuration we're on. And also with that, we can include different files into our project. So for C++, we have a few meta build systems to choose from. We have CMake, which for some reason is the unofficial de facto standard in the industry. We also have Sharpmake, which lets you write the build scripts in C#. We also have Premake that does the same thing, but with Lua instead. We have Meson, and we have Nen. A quick reminder of the remaining problem left unsolved when we're using the Pimpl idiom and also handles. We've essentially have two definitions to one declaration and broken ODR. So how do we utilize the meta build system to solve this remaining issue and have our program compile? Looking at the example, I've opened up. So in the example projects, I use CMake. Inside of CMake presets.json, what I've basically done is added two configurations, right? One for Vulkan, the other for DirectX 12. Now, depending on the configurations, I've set different values to these variables, right? So for Vulkan, use Vulkan is set to true, and use DX12 is set to false. For DX12, I've set use Vulkan to false, and use DX12 to true. inside of my project's CMake script, first I include all the files necessary for the project. But depending on the value of these variables, I am going to include different CPP file, right? So taking our previous example into account, right? Remember that we have a device.cpp in one of each folder, one in Vulkan and one in DX12. If use Vulkan is set to true, I include device.cpp from Vulkan, from the Vulkan folder into our project. But if I have used DX12 to true, I include device.cpp from the DX12 folder instead. And what this does that, if you're using Visual Studio, I can select the configuration over here, right? Right now it's on Vulkan, and it is including device.cpp from the Vulkan folder. But if I swap this out to DX12, and I open the project, it is going to include device.cpp from the DX12 folder. And essentially, we no longer have the problem with ODR, because our project only sees one device.cpp file, right? And same thing again, inside the way how we consume the API is that we would just take the interface and call the method. So if I build this, it's going to compile. There's nothing to work. There's no work to do because I've already compiled beforehand. The thing about doing what we did before this is that you no longer have the ability to swap out implementations at runtime. If you recall from our discussion on runtime polymorphism, it's something we can do, right? We can swap out implementations at runtime, but with using meta build systems to alleviate our use of the Pimpl and handle method, we lose that. So is there a method that we can use to support swapping out perform implementations at runtime? But the bigger question is this really an important feature? Because generally you only ship binaries that are required for a specific platform, right? And there are very few exceptions to this rule. One being graphics API. But the other thing, and I haven't seen any software doing this, but you could maybe provide different data streaming solutions depending if your software is being installed in a hard disk or SSD. It would definitely help with stream times. But these are the few exceptions to this rule. And generally, swapping out implementations at runtime adds so little to the business value for the amount of work that it takes to get right. But this is a design pattern talk, right? We have to at least know how to do this. So in case if some requirement comes up in the future and we have to do this, we already know. Thankfully, there is a feature from the operating system that lets us do this, which is by using shared libraries, DLL, right? Because in a shared library, the symbol used by a program can be loaded from a shared library into the program's memory at load time or runtime. Now, in order for hot swapping to work, you need the ability to load in the symbols at runtime. Since this is a software design talk, I'm not going to cover anything about DLLs. In fact, there is a better presentation from James McNellis that explains everything you ever wanted to know about DLLs. I think it was from CppCon a few years back. I highly recommend his talk if you're interested to know how DLLs work. So reusing our previous method, let's try making our abstraction layer into a shared library. Now, I've basically divided this. I've basically extracted out my abstraction layer into a DLL, as you can see over here. It is now a shared library. And I am on the X12 at the moment, but I'll switch back to Vulkan because I like Vulkan. Of course, the UI is not being updated, so let's just update the UI. Now we have device.cpp from the Vulkan folder. And inside of device.h, you can immediately notice that a lot of things have changed. Our device is our methods are no longer member variables of a class. Instead, they are now free functions. And our device just contains, it's just a struct that contains the forward declared device context. As usual, inside of device.cpp, I've provided the definition to device context. But, you know, what's up with this, right? So the thing about loading in symbols from a DLL, in order for it to work, the names of the symbol cannot be mangled. And if you have these functions as member functions to a class, their names will be mangled. And generally, it doesn't work with methods of a class. I've tried; it just doesn't work. Also, we have to declare these methods as DLL export. So essentially, we just do the same thing as what we did before, except that we've broken this down to more of how you would do it in C. Aside from that, I've provided aliases to the function pointer's type. So for device, I provided an alias to the function pointer, which is device initialization fn, and also to get a device type, I provided an alias device API type fn. Inside of the device.cpp file, same thing again. I've instantiated an object of device context and assigned the and store reference to the object in memory. I initialize everything, right, with all of Vulkan's verbosity, and then I return a device that contains that stores an address to the object in memory. And then inside of a different project where I am using or I want to load in the interface at runtime, basically what you need is some sort of project configuration loader or a project configuration bootstrapper that lets you load in the DLL depending on the value that's set inside of the configuration file, right? So as you notice, inside of config.json, I have an API key that contains the Vulkan value, that contains the value of Vulkan. And depending on the value that's being stored inside of the configuration file, I will then load in the DLL. So over here, I am getting the value. I'm getting the API. And depending on the API I've selected inside of the configuration file, I will then load the necessary DLL. Once I have a handle to the DLL and it is valid, I then load in the symbol, right? I then load in the symbol from the module. getProc_address is a Windows method of loading in a symbol from a DLL. And then I'd have to cast it to the function pointer's type. Now, if the symbol does exist, I then initialize the device. And basically, you pretty much do the same thing for every single method of the interface. So, a quick demo of how it would work. So over here, I have a config.json file that is currently set to dx12. If I run the executable, it's going to load in dx12 runtime device.dll. Oh, my bad. I should be running the executable, not the DLL. So we've successfully launched the window, and we can see that the type of device that's being instantiated is dx12. Now, if I change this to Vulkan, obviously with this you need error handling in case if the value that's provided to the key is not correct. But that is out of scope of this project. So if I run the executable again, it's going to load Vulkan runtime device.dll. You can see we've successfully opened the window, and the device type that is being used is Vulkan. Oh, I've accidentally skipped this, but basically I've pretty much explained this part. In the example, right? So the requirement is the executable needs to at least know about all the declarations for the interface. That's why we have the header file, device.h. Usually done by exposing a header file containing the type alias for the functions. I have seen certain libraries that expose variables, the function pointer variables, and when they load in the symbol, they assign the function pointer variable to the loaded symbol. As already mentioned, on Windows, DLLs can be loaded in at runtime with load module, and then you can get the symbol to the function with get proc address. Now, this method sounds really good and all, but making things work in runtime exposes runtime problems. And whenever you want to swap out implementations at runtime, first you need to make sure that the symbol that is already loaded in is not being used while the implementation is being swapped. And in a single-threaded program, this is not really a problem, but most softwares these days are multi-threaded, and there really is no guarantee that there really is no method that you can guarantee to have all of the threads stop using the implementation at the same time. It gets really difficult to do so. Also, there is the possibility of the interfaces not matching. You could have an updated or an outdated header file, but an updated DLL, and vice versa. I've already mentioned it does not work with class member function because C has no notion of member functions, and the names need to be unmangled for you to invoke, for you to get the procedure's address. And the thing about swapping out DLLs at runtime, there is the possibility of your program crashing. So ultimately, to support this feature, it does introduce some experience breaking problems, right? And it is a feature that requires a lot of time investment. So generally, if you can avoid this, you shouldn't be doing this. But just know that it is a method that you can. This is a method that you can use if you choose to do. Finally, we're going through some tips and tricks, right? It's been a long day. Let us wrap this up really quickly. And I think I am reaching the time limit for my session. So let's just get this over with really quickly. So I've already mentioned throughout the presentation that the problem with writing an abstraction layer for cross-platform development is that the different platform do the same thing basically, but there are a few things that make them very distinct from one another. You've already seen Vulkan is very verbose as compared to DX12, and I'm pretty sure that's how it is in different fields as well. So you normally have a problem when you'll probably have a problem when you're designing the interface, and usually the advice that I would give is that start off with one platform and design your interface around that platform, right? If different platforms are similar to one another in terms of specification, they should not diverge by a lot. And usually, to be completely safe, you would write your abstraction layer around the most verbose API. That way, for things that for platforms that are much simpler, you could have specific edge cases or specific functions that cater to the verbose API do nothing for the simpler API. Also, with writing abstraction layers or for cross-platform development, documentation is your best friend. I always have my second monitor filled with the docs from DX12 and Vulkan. Always refer to documentation, and this is an advice that should be taken into heart before you actually start implementing the interface. You should really document how you want the interface to look like or feel like, because if you document prior to writing the interface or writing the abstraction layer, it helps you build a mental model of what your interface or your API should look like. And that gives you better clarity on what to work on or what to work around. Also, it is good practice to constantly iterate on the design of the API or interface. Ideally, you want to make your abstraction layer as easy to use, even for yourself, right? Because let's be honest, if you don't find it nice to use, chances are that other people aren't going to enjoy using your API as well. So, as conclusion, and as closure to my presentation, we've gone through the introduction of abstraction and also cross-platform. I've also explained to you why you might want to have an abstraction layer when you're doing cross-platform development. Also the challenges. I've also gone through all of the patterns, all of the methods that you can use to create an abstraction layer for cross-platform development. We've talked about using preprocessor macros, on why it's very easy to start with. We've discussed the pros and cons on how you should avoid from preprocessor macros as much as possible. We've talked about runtime polymorphism. We've talked about the vtable and how you would implement it in code. We've looked at code samples for it and why you shouldn't be using runtime polymorphism, right? Table is an expensive thing. We've also talked about creating our abstraction layer using handles and Pimpl, and how the default method without using meta build systems would cause problems with the one definition rule. We've then talked about meta build systems and how it helps solve our issues with ODR when implementing our abstraction layer with handles and Pimpl. And we've talked about attempting to change implementations at runtime. And we've discussed why you shouldn't be doing this. And lastly, most recently, I've given you the tips and tricks that I personally use when creating an abstraction layer for cross-platform development. So with that, thank you for your time. I hope this presentation would serve as a guide for everyone who needs to create an abstraction layer. Again, sincere apologies for not being able to attend. To be honest, I really wanted to be there with you guys, but it is what it is. We'll have to make do with our current situation. I hope you enjoy your talk. Apologies for not delivering a smooth presentation. It is my first time. I am very nervous, just so you know. With that, thank you and have a wonderful rest of the day.